Hello there. I would like to talk to you today about a mains LED lamp drive circuit. You see the schematic of this circuit in here. Okay. It consists of a 2 microfarad 400 volt decoupling cap, a bleeding resistor for that cap, 680 kilo ohms. You have a bridge rectifier made of 4 diodes. They are the 1N4007 diodes. The ratings for these diodes are about 1000 volts, 1 amp. The IF is 1 amp, and the breakdown voltage is around 1000 volt. You have a smoothing cap, electrolytic smoothing cap. It's a 47 micro 50 volts, and another bleeding resistor associated with it. And you have a 16 LEDs in series that make up the lamp. And the hardware for this circuit is, as you see in here, that's the AC decoupling cap, and that's the smoothing cap, electrolytic smoothing cap, and you have the 4 diodes in there and the 2 bleeding resistor, and you have those 16 LEDs in series that make up the whole lamp. Okay, so this is the hardware and this is the schematic. Let me start at what kind of measurements I made on this circuit. I just used a regular meter. It's not something really sophisticated, nor an oscilloscope. I don't have an oscilloscope, so I assume some of the wave shapes and voltages according to the logic and analysis I see. So let's start first by the mains voltage. The mains voltage that we have here in Jordan is a 230 volts. That's the VAC. The IAC, as was measured, was 116 milliamps. The voltage across the decoupling cap was measured to be 207 VAC. The ripple voltage across the smoothing cap, the storage and the smoothing cap in here, was 3 volts. The voltage across the smoothing cap, the DC voltage across the smoothing cap, was 50 volts. That was AC, of course, and this is a DC. The current passing through the LED series was measured to be 100 milliamps. It's not really much different than the one in here. They are very close anyway. The power of the series of these diodes put together is the 50 volts multiplied by the 0.1 amp equals 5 watts. The power into the circuit from the mains equals to 27 volt amperes, and I said that because we have a reactive power in there. We are not consuming the 27 volt amperes. It just gets into the circuit and leaves most of it. And you have the voltage of the LED, which is for each individual LED. It's about 3.125 volts each. So the total of them add up to the 50 volts DC. The frequency, the mains frequency, is 50 hertz. So each cycle is 20 milliseconds. It's not like the States, 60 hertz. We have a 50 hertz here in Jordan. It's easier to divide and multiply. Okay, so this is the measurements, and this is the circuits, and I'll try to explain how it works Okay. The idea that you charge that decoupling cap, okay, and after that you discharge it to the load, which consists of the smoothing cap and the LEDs themselves, through the diodes. Through the charging process, we use D3 and D4 in the charging. And while discharging at this part, all the way down to the minimum peak, we use D1 and D2, or D1 and D2 are used. Now, how does the circuit operate? We start first by putting voltages in here. The peak voltage for the mains is a 325 volts, which equals the 230 multiplied by the root square of 2, so that gives you the peak. Okay. And as you see in here in the schematic, you notice that the voltage of the decoupling cap added up to the voltage of the smoothing cap would equal to the mains voltage peak. We have to ignore the voltages of these diodes, and we consider the diodes when they are on, consider them to be short, equals to 0 volt, and when they are off, we consider them open. Okay, so the mains voltage in here, the peak voltage, would equal to the voltage of that decoupling cap added up to the one, the smoothing cap. The 50 volts in here, ignoring the ripple voltage, is always there. So you have the 50 volts in here, okay, deducted out of the 325 volts in here. You left with the 275 volts, which is across the decoupling cap. Now, while going towards the peak, and that cap was charging, see here, okay, as we see in here, okay, going toward the peak, this decoupling cap will be fully charged with the polarities that you see in here. Okay, and that describes the situation. V equal to 325 sine 90 degrees. Okay. Now, let me line the paper. Okay. Now, as the mains voltage starts dropping, you won't be having the same voltage that we already have in here, which is the 50 added up to the 275, which equals 325. Now, once the mains voltage starts dropping, you won't have that voltage available no more, and that will shut all the diodes off. Okay? So that's, let us say that the blind spot at this time, where everything just works on that smoothing cap. That smoothing cap has to supply all the energy to the circuit, and you can consider the load to be fully disconnected from the supplying circuit at this moment. Let's call it the blind spot at this moment. So as the voltage starts decreasing, the mains voltage starts decreasing, okay, until you reach that moment where it becomes, where the voltage across the mains becomes 275 volts, okay, that would allow the switching on of D1 and D2. While we're going up, D3 and D4 were in operation. In here, this is the dead area, the blind spot. Nothing would work, which equals 50 volts, the same as that cap in there. And after that, we switch the diodes. That's the reason, okay? And like we said, the state of the cap would be like this in here. This one in here. And that's why when this terminal was going down, forced down by the mains, this terminal will follow. And when it follows, it will turn on D3 and, it will turn on D1 and D2, as we said before. And this case will continue as the mains just pulling down that C1 until they reach this point, the neutral point, where the mains voltage equals 0. And in this case, the polarities, no charge will be available on the decoupling cap, no charge on the right plate or the left plate. And after that, as the mains going down again, the process start inverting, as we see in here. Okay, where the left plate start having a negative charge stored on it, and the right plate a positive charge start on it, and D1 and D2 are in operation, and that will continue until we reach the bottom of that negative peak. And the same thing happens as was happened up there. Same thing. You have another blind spot in there where you switch your horses or switch your diodes, and you start riding on D3 and D4 again, and you have that blind spot where the cap, smoothing cap, has to supply all the energy to the load. Okay, this is how the circuit operates. So the idea that the mains are controlling or driving that decoupling cap and doing all the magic in the circuits. It's really a simple yet a very reliable circuit. It really works nice. Okay, let's see. We can have more number. Here's the currents in here, as I assume they are. During this part, we have D1 and D2 are in operation. And of course, it's not that smooth. It won't be that smooth. Especially once you switch it exactly at this moment in here. When you switch the decoupling cap after the black spot or... Okay, so you have a little bit of surge in here. You won't have it won't be smooth. Maybe it's a little bit peaky, as a matter of fact. But since I don't have an oscilloscope, I don't know how it looks. The average of it is about 100 milliamps, as we said before. Okay. That's the I of the IC2 plus the I of the LEDs, roughly 100. Okay. And what else we have in here? Let's say some measurements for the energy of the caps. The capacitor energy, as we know, it equals 1/2 CV squared. So for every 10 milliseconds we have, the energy stored will be 1/2 the 2 microfarad multiplied by the 275 volts squared. That's equal 75 millijoule. We are talking about this area in here. Okay. And it's discharged here. And charged again from here to here. And discharged here. And charged from here to here. Okay. So here it's charging, discharging, charging, and discharging. Charging again. Okay. So that's in a second. If we calculated that in a second, we'll have about 7.5 joule. Or since in a second it means 7.5 watts. What we actually getting is about 5 watts in here and 7.4 watts. I don't know where it's lost. but it's near enough to the 5 that we have in here. And that's probably the idea of selecting that 2 microfarad decoupling cap in the first place, to make sure that it would store enough energy, okay, enough to cover the need of the load. And we see in here it covers it real well. And what else do we have? Yeah, we have the voltage of that VC1, as I expect it is, as I expect it would look like. It goes all the way up to 275 volts, okay, and then it flats. This is a real flat, okay. This is the dead area, or the blind spot as I called it, okay. The time for it can be calculated. Probably it's a fraction of a millisecond, or probably no, it won't get to a millisecond. It can be calculated. And this one in here, another blind spot in the bottom too. And as we see in here, the voltage of VC will reach to 275 volts. Okay. And again, it goes down to minus 275 volts. Another thing to talk about, the voltage of that smoothing cap. And I said again, I didn't use an oscilloscope to see how it looks like, but I assume something like this. We have a 3 volts in there. That's measured RMS, measured on the meter, not a true RMS, but it considers it as a sinusoidal wave, so it measures 3 volts. Now converting that to a sawtooth that we have in here, we multiplied the V peak multiplied by 3 by the root square of 3, that equals about 5.2 volts, so that's the peak. So it's peak to peak, it's about 10.4 volts, and I assume something like that. Up charging all the way, blind spot after that, well, where you have that smoothing cap had to supply that energy for this duration. Okay, it's not a long duration, like I said, maybe it's less than 1 millisecond. And we have the charge again and discharge again, the blind spots. Okay, the joint is not that perfect, but you know, it gives you an idea for what's happening. And this is all I have. I hope that was good enough. And I hope what I said was useful. And thank you for watching. Bye for now.